Hi everyone, welcome back to the part 2 of metallic bond. So in this part, we will be discussing about the band theory of metals. Okay. Let's move to the band theory of metal. So metals are described as having a luster, good thermal and also electrical conductivity, and they are very malleable. So here, what do you understand about luster? Luster means shiny, berkilat, and malleable means it can be shapen without breaking it. Maksudnya you boleh tarik, you boleh shape without perlu breaking it. Okay. Then these properties, okay, are actually direct results of the ability of the atom to contribute electrons to a common cloud around the atoms. So these facts actually indicate that the bonding in most metals is both strong and non-directional. The mobile electrons can conduct electricity and heat. Okay, so from the electron C, okay, you know that actually metal can conduct electricity and heat because of the existence of electron C. So this band of theory is actually a related model that gives a more detailed view of the electron energies and motion is the band model. This is what we call band theory of metals, or sometimes as you know as the molecular model, or MO. This is what we have discussed last week. So these two atomic orbitals interact. When they interact, whether they interact end to end or side to side, these two widely spaced molecular orbital energy levels will form what we call bonding and also anti-bonding. Okay, as you can see from this diagram, this is what happens when two orbital interact. They will form a bond here and also anti-bonding. Okay. So this is what happens when you have more than two orbitals overlap or two orbitals interact. Okay, when many metal atoms interact, so as in a metal crystal lattice, a large number of the resulting molecular orbitals become more closely spaced, and finally they will form what we call virtual continuum of levels. This is what we call bands. Okay. So from the molecular orbital theory that we have learned before this, okay, interaction or overlapping of orbitals will form bonding and also anti-bonding. So here, okay, as you can see, this is the non-bonding, or usually we can consider this one as lone pair. Okay, so this is one of the example of virtual continuum of levels or bands. Okay, for example here, let's say we have magnesium. Okay, magnesium. For example, we have a magnesium lattice. Okay, the number of atoms is in even a small piece of magnesium metal is very large. Okay, up to 10 to the power of 20 atoms. Okay, for example, let's say this is a small piece of magnesium. Okay, and the atom here is 10 to the power of 20 atoms. So what happened to these atoms when we have large number of atoms here? Okay, so what happened? The orbital will start to interact or start to overlap between each other, right? So the number, therefore, the number of molecular orbitals they form is also very large. Okay. So, what is the proton number for magnesium? It's 12. Okay. So, you will have the electron configuration of 1s2, 2s2, and then 2p6, 2p6, 3s2. Okay. So, here, alright, as you know, the magnesium will have, okay, magnesium has two valence electron from this electron configuration. Okay, and 3p orbitals are empty, so this magnesium will have 3p0 empty, And when many of these orbitals interact, two types of bands can be formed. Okay, two types of band can be formed. So here, alright, because the 1s, 2s and 2p orbitals of the period 3 atom are filled with core levels, so they do not interact strongly with the corresponding orbitals on adjacent atoms. Okay, they will form rather narrow bands that are well separated in energy. Okay, this is what we call a band gap. Okay, the energy difference between the highest level to the lowest level, because they extend farther from nucleus, jauh daripada nucleus. Okay, this is what we are talking about, the 3s and also the 3p. The valence orbitals of the adjacent atoms interact much more strongly with one another than do the field core level, so it will form a larger bandwidth. And the bands here derived from the 3s and 3p atomic orbitals are wider than the energy gap between them, so the result is what we call overlapping bands. For example, okay, this is example for magnesium. Okay, magnesium, aluminium and also sodium. Magnesium, aluminium and also sodium. Okay, here sodium we have 11, magnesium we have 12, while for the aluminium we have 13. Okay, so from the 1s to the 2p, 1s, 2s and the 2p, it will form what we call core bands. While for the 3s, 3p here, this is where we have the valence electron. We call it as valence band. And the gap between 1s to 2s, 2s to 2p and 2p to the 3s, this is what we call the band gap. Okay, as you can see from this diagram. Okay, right. So here is an example for sodium. Okay, so for the sodium we have 3s1, right, until 3s1. So this is the core electrons. Okay, and this is the overlapping between s and p orbitals, and this is the overlapping between s and p orbital. This is the p0. Okay, as you can see here, this is where we have one electron, one valence electron with a 0 electron at the p orbital. So this band theory of metals, you need to know about two kinds of bands. Okay, first one is valence band. What is valence band? This is where you have the molecular orbital energy levels, okay, filled with electrons. Okay, for example, for magnesium, the valence band is actually located at the 3s orbital. And second one is the conduction band. Okay, this is where the empty molecular orbital energy levels. Okay, so for example, magnesium, okay, this conduction band is actually formed by the overlapping of the empty 3p orbitals. Okay, when you have electrons, this is what we call valence band. When you have empty molecular orbital energy levels here without no electrons at all, for example, for magnesium is the located at 3p. Okay, because of these two bands, okay, it will form three categories of materials that you can or you may be easily understood by the energy gap, okay, between bonding bands and also the anti-bonding bands. Okay, there are three here. Okay, three categories of material that will be formed. Okay, there are three categories of material that can be understood by the energy gap between bonding bands and also the anti-bonding bands. Okay, there are, first one, if you have a large gap in energy, the material is called as insulator, penebat. If the gap is finite but small, then the material can be called as semiconductor. And if there is no gap at all between the bands, okay, between the bonding and anti-bonding, or the valence, if there is effectively no gap between the bands, okay, no gap at all, so the materials are called conductors. So these are three diagrams, okay, that show you the insulator, semiconductor, and also conductor. So as you can see, the insulator, we have here a large band gap between valence band and also conduction band, and we have a small gap between semiconductor, and we have no gap at all between valence band and conduction band for conductor. So guys, that's all for this chapter. It is a short topic for this code, and I have 3 exercise for you. So please answer for question 1, 2, and also 3. We will discuss during our virtual class next week. So that's all for today. So I hope to see you again on the next video. So please like, comment, and subscribe my channel. Thank you. Bye.